Camera changes with the distance. If you get a well-focused picture, that doesn't mean you'll get a well-focused picture here. Okay. So folks, today, in the last class we saw what happens if there is autocorrelation in the data and how does one correct for autocorrelation, especially the first order autocorrelation. We did a feasible generalized least square, right? Okay. Today, we will learn about a very famous test which has been famous since 1951 of first order autocorrelation in the data. So if you suspect first order autocorrelation, what do you do? Right? Okay. This test is called the Durbin-Watson test. This test is called the Durbin-Watson test. Durbin-Watson test. The test of first order autocorrelation in the data. Okay? Right. How does one take this test? So you have a regression, for example, yt is equal to alpha plus beta xt plus et. Okay? And you suspect first order autocorrelation. That is, you suspect that et is phi et minus 1 plus vt, plus where vt is a normal distributed random variable, mean zero, constant variance, and no autocorrelation. Right? Okay. Now, how does one test for this hypothesis? So step 1, calculate calculate y hat and yt minus y hat e hat t by running this regression and obtaining alpha hat and beta hat. You do this regression, obtain alpha hat and beta hat, then calculate e hat t's, which is yt minus y hat t. Sure? Right? Then, once you have done that, consider, once you've done that, consider this quantity. Okay? What this be? This will be e hat t square plus e hat t minus 1 square e hat t minus 1. Okay?
Would it be minus 2 e hat?
It will be minus 2, you're right. Sure, correct. It will be minus 2 e hat t minus 1. Okay? Think of summing this whole thing. Yeah? Right? Which will be okay? Now, this and this are not really terribly, right? There have to be some here. I'm sorry, this will have to be plus summation minus. Right?
Yeah.
Okay? Now, this and this will not be terribly different from each other. Because, what is this? This really goes from t is equal to, start from the second observation to capital T. the number of observations you have, because this will start with t minus 1, so you can't start from the first observation. Right? So it is going to be t is equal to 2 to t is equal to 2 to t. Yeah? So this and this will differ just by 1 observation square. And so we can roughly regard this and this as the same quantities, approximately. Right? Because this is sum of E hat t squares. This is the same sum except one quantity. Except one quantity. So we can then write this as being equal to, right? So this quantity can be written as being approximately equal to 2 yeah? Sure? Right? Everybody at the back can see this? Okay. So now, let me divide throughout by E hat t minus 1 square. Let me divide throughout by E hat t square. Let me divide throughout by E hat t square. Right? So what I get is, if I divide this way by E hat t square, I get summation E hat t square upon summation E hat t square, right? Minus 2 or let me divide by E hat t minus 1. I think it's better to divide by E hat t minus 1 square. Okay? Now this and this is almost identical. Okay? This quantity almost identical. So this will be equal to approximately 2 minus 2 into you see this point? Now can somebody tell me what is this? What is this? Covariance between ET and ET minus 1. Right? Covariance between ET. And what is this? This part is covariance of ET minus 1. This is the variance of ET. So this is the correlation between ET and ET minus 1. In fact, remember, if you did the following regression, ET is equal to phi, yes? Then what will be the estimate in general for xy? Suppose this were y and this were x. What will be the estimate of phi here? For a simple regression, suppose if you think of this as yt and think of this as xt, what will be the estimate for phi? Summation xi of xt yt upon summation xt square. Right, so in this case it will be summation et minus 1 on summation et minus 1 square. Right, these are all estimated values, which really is an estimate of phi hat, right? You see the point? Because if this is y, this is x, beta hat is given by summation xi y upon summation xi square. It will be summation e hat t minus 1 upon summation e hat t minus 1 square will be the beta hat. In this case, that's phi, right? So this becomes approximately equal to 2 into 1 minus phi hat, right? Because this becomes phi hat, 2 comes out common, so 2 into 1 minus phi hat. This is called the Durbin-Watson statistic. Okay? Now there is no autocorrelation. If there is no autocorrelation in the error terms, that will mean, what will be the value for phi if there is no autocorrelation? 0. Phi would be 0 if there is no autocorrelation. So what would be the value for the Durbin-Watson statistic? 2. So if the Durbin-Watson statistic is 2, it would indicate that there is no first order autocorrelation in the data. Is it clear? But what are the values that phi can take? Phi can take values between -1 to +1. So there is perfect